Oh, good afternoon. What a great introduction to this topic. So today I'm going to be talking about collisions of differentiated bodies in the early solar system and kind of focusing on this mixing of liquid iron nickel and silicates. And this is constrained by a single crystal paleomagnetism. So first I'm just going to briefly touch on what's already been mentioned, this work done by our group on main group pallasites on the paleomagnetics and the resulting conceptual model of pallasite formation. And then I'm going to discuss new data from Eagle Station. Eagle Station is a pallasite as well, but it's thought to originate from a separate parent body than the main group pallasites. Briefly, I'm going to touch on some preliminary data on mesositerites, which are a separate class of stony iron meteorites. And then finally, I'm going to just bring it all together and sort of ideally talk about the advances on our understanding of the early solar system based on this new data. So as has been mentioned, we have main group pallasites. These are composed of metal and olivine phases. The olivines can be up to a centimeter in size, gem-like, and can be gem-like in quality, and do not show evidence of shock. The metal phases are mostly either a low nickel camosite or a higher nickel tianite phase. An early hypothesis on the pallasite formation suggested they may have occurred near the core-mantle boundary. If there is a magnetic record, though, this may preclude this core-mantle boundary hypothesis. Magnetic experiments on meteorites in general and pallasites in specific are challenging. There's a range of magnetic grains in the metals that range from single to multi-domain in size. Magnetically softer multi-domain grains can acquire recent stray magnetizations and are unsuitable for study of the early magnetic history. Our group's approach is different. We look at the magnetic inclusions contained within isolated silicates. In the case of pallasites, these are olivines. These are minute inclusions which have single domain-like properties. We can see this here in hysteresis plots of Esquel and Imilac main group pallasites. These show little effect from anisotropy and are ideal recorders of the paleomagnetic field. Here we have microscope and transmitted light and scanning electron microscopy of the main group pallasite olivines. And we see these chains of metal inclusions. These range in size from 200 microns down to submicron in length and are iron-nickel sulfide in composition. When we do compositional study, though, and here we see in a backscatter and we have compositional mapping in EDS, we see subdivisions into iron-nickel and iron-sulfur-rich zones. These subdivisions are on length scales that are appropriate to retain magnetizations on billion-year timescales. Paleomagnetic experiments, these are thermal demagnetizations as well as paleointensity on Esquel main group pallasite. Here we have the orthogonal vector plots, and we see a relatively simple, straight component of magnetization. Paleointensity experiments, here we have a Tellier-Co and a total TRM, suggest a paleo field recorded by Esquel of about 110 to 119 microtesla. Similar experiments on Imilac pallasite suggest a paleointensity of 70 microtesla. This is a fairly high value and suggests it was acquired in the presence of a dynamo. But these results have motivated a new conceptual model of pallasite formation, where we have a differentiated parent body with a liquid iron-nickel core that hosts a dynamo. And this is hit by an impactor that is differentiated as well. So we can see that here. And then we have the metal from the impactor mixing with the silicate mantle through we have these dikes of the metal from the impactor and the silicate mantle. And this gives the pallasites their characteristic metal olivine texture. Small fractures in the olivines can open up and are injected with metal. This is what retains the magnetizations that we record in our olivines. So main group pallasites isotopically have here we see oxygen isotope schematics, and they fall near the terrestrial mass fractionation line. Eagle Station pallasites, though, here in oxygen, and here we have oxygen and chromium in the isotopes, we see a very distinct difference from main group pallasites. Here we see Eagle Station, and here is main group and the main group. On the basis of these different isotopic compositions, it's suggested that the Eagle Station originates from a different parent body than the main group Pallasites. So here's the actual meteorite we looked at from the Eagle Station Pallasite. This was provided by our colleagues at the Vienna Museum of Natural History. We've done scanning electron microscopy investigations of the olivines from the Eagle Station Pallasite. These show similar metallic inclusions of iron-nickel sulfide to what we see in the main group. Particularly, we see these subdivisions into iron-sulfur and iron-nickel rich regions. These are, again, on subdivisions that are small enough to retain magnetizations for billions of years. This is magnetic hysteresis work on olivines from the Eagle Station Pallasite confirmed the presence of single-domain-like recorders that are ideal for paleomagnetic study. However, unlike main group Pallasite, the natural remnant magnetizations of the Eagle Station Pallasites are much weaker, approximately an order of magnitude. To measure these, then, this requires the use of a new magnetometer. This is a highly sensitive DC squid magnetometer with a small bore configuration. The small bore allows the sensing coils of the magnetometer to be that much closer to the samples, which allow us to measure these weaker Eagle Station olivines in contrast with the stronger main group Pallasite olivines. These are the results of our thermal demagnetization experiments on Eagle Station Pallasite olivines. And what I want to point out, hopefully it's quite obvious, is they have a very different structure and directions than we saw in the main group Pallasites. We see multiple components of magnetization. I've drawn some arrows to try to highlight these. We have a lower temperature component and a higher temperature component. There's also evidence that there might even be a third component of magnetization, but it's not very well resolved at this time. So these multiple components motivate some new hypotheses on how they could have arisen. One, we could be looking at a time-dependent effect. As the olivines slowly cool, if the dynamo changes, this might have been recorded. Another hypothesis is that instead we're looking at a dynamo field that's been affected by an impact event, partially resetting the magnetization. I should stress, though, that these are not mutually exclusive hypotheses. However, due to the lack of cooling data available for Eagle Station Pallasite and our paleomagnetic data, we elected to investigate evidence for shock. This was done in a thin section microscopy by Ed Scott. We're looking at the metal phases of an Eagle Station Pallasite. It's been cut off, but this is at 5x magnification. At this length scale, it appears that the Eagle Station Pallasite metal resembles main group Pallasites. However, at higher magnifications, this is no longer the case. The cloudy zone taenite is heavily disturbed and only wispy remnants of it remain. The tetrataenite rim is also altered, and in the pallacite field, we see evidence of spheroidation. Taken together, this is evidence for a shock heating that might have been up to 320 degrees Celsius. So we'd like to investigate the paleo fields that can be recorded by these different components of magnetization in the Eagle Station Pallasites. However, as a caveat, I should point out that there's a magnetic shielding effect due to the metal phases of the Pallasites, so that the paleo intensity recorded within the olivines is going to be a conservative minimum estimate of the field strength. Still, though, we can and did do paleointensity experiments on these different components at the lower temperature interval that may have been affected by shock on the basis of petrologic data. This records a fairly weak field of 11 to 20 microtesla. When we focus, though, on this higher temperature interval, so here in this plot I've got these red arrows showing the temperature interval that may have been affected by shock, and then a higher temperature component. The paleo intensity, so this is a total TRM experiment, on this higher temperature interval that has not been affected by shock records a fairly high value, 56 plus or minus 14 microtesla. This suggests it may have also been acquired in the presence of a dynamo similar to main group Pallasites. So this summarizing what we've learned now about Eagle Station, we have evidence, petrologic and paleomagnetic, that suggests that it's undergone a late impact event after pallasite formation. However, at higher temperatures, we see that a strong field was recorded, suggesting it was acquired with a dynamo. So moving on to mesositerites, these are a separate class of stony iron meteorites. They may have formed in a similar manner to main group pallasites. However, previous paleomagnetic work on metal and silicate phases, such as that done by Collinson, show a lack of consistent directions. We focused instead on olivine class. These are fairly rare, up to a centimeter in size, and may host minute magnetic inclusions that are more suitable for paleomagnetic study. This is very preliminary work, but we have thermal demagnetization data. After removal of a lower temperature viscous component, we still see a stable remnant magnetization. In the paleo field, this is in a total TRM experiment, of this higher remnant magnetization is about 52 microtesla. This is another high field suggesting it was formed in the presence of a dynamo. So, summarizing everything together, and this is kind of building on what we just heard, what we see is in Eagle Station pallasite, we have a multiple component signature of magnetization, and while the low temperature component may have been affected by shock and it records a fairly low value, this higher temperature interval suggests it was acquired in the presence of a dynamo. And we are arguing that the Eagle Station pallasite formed in a manner similar to the main group, but I'm going to stress again, comes from a different parent body. As well, it's worth emphasizing that Eagle Station, on the basis of our petrologic and our paleomagnetic data, formed in the upper mantle of its parent body and not near the core-mantle boundary. As well, we have preliminary data on mesositerites, which also may have formed in a manner similar as pallasites, but even at shallower depths in its own parent body. But this is the real core, and I think this, again, builds on the talk we just heard, that our evidence suggests that collision between differentiated bodies in the early solar system that may or may not have hosted dynamos was a frequent event. Particularly, though, this injection of liquid iron-nickel core material from impactors into target bodies is one that likely occurred many times in the early solar system. Thank you.
There's time for questions. Come on, don't be shy. Okay, perfect.
I wonder, in this model of injection of the liquid nickel core material into the crust, how you explain that really the only mineral that's found in these is olivine. Where are the other minerals you might expect under that scenario?
So in the case of pallasites, we're thinking that these are forming in the upper mantle, which is going to be mostly olivine in composition.
And so, but entirely, okay, yeah.
At least, I mean, we have a limited record of what's available. I mean, this is the challenge with meteorites in general, right?
Yeah. Thanks, yeah.
More questions? If not, thanks again.